In this lesson, we're going to be briefly reviewing the ways in which the body manages heat and the disorders associated with heat and cold stress. What we're going to look at in detail are quantitative measures of heat stress, how to do the calculations, and various controls for heat stress. We're going to say very little about cold stress other than to mention the disorders and the general concept of the heat balance. I'm sure that you all recall that the body is maintained at a constant temperature of around 37 degrees C. The control is done by an organ at the base of the brain called the hypothalamus, which causes certain involuntary regulatory mechanisms to take place if the temperature gets out of balance. The maintenance is usually done within plus or minus 1 degree C, and we begin to see effects at plus or minus 2 degrees C. The involuntary regulatory mechanisms include the blood circulation. More blood to the skin releases heat from the core of the body. Less blood decreases heat loss. There's a large difference in blood flow from normal, which is about 300-400 milliliters per minute. When the surface blood vessels dilate, this can increase up to a factor of 10, and when they constrict, it can decrease by a factor of 10. So there's overall about a factor of 100 difference in blood flow to the surface of the body, which is a very effective control. Another involuntary mechanism is sweat evaporation, which we'll talk about in detail. And then on the cold stress side, there's shivering, which increases metabolic heat production in an involuntary way. Most well-known cold disorders include frostbite, freezing of skin, which has several degrees of seriousness and often is caused by a combination of cold temperature and wind conditions. Then there's also hypothermia, which is whole body cooling and can be fatal in some circumstances, as I've said here, at less than 29 degrees C, but that's also a factor of time. So these are just approximate numbers, of course. Let's also review some of the heat disorders, starting with skin rash or heat rash due to prolonged sweating, where the pores in the skin become clogged up in the sweat ducts. The area may become reddened and may itch or hurt and cause various skin eruptions. Heat cramps are due to a loss of salts in the blood and muscle tissues due to excessive amount of these salts being lost in the sweat. The cramping may be in either skeletal muscles or involuntary muscles such as abdominal. It occurs perhaps several hours after the heat exposure and can be pretty severely painful. Heat exhaustion and heat fainting is both caused by insufficient blood flow as the blood vessels dilate, and lack of volume due to dehydration can cause pretty much symptoms similar to shock. The last one is heat stroke, which is the most serious heat disorder and is characterized by a breakdown of the regulatory mechanism in which the person ceases to sweat and their temperature just climbs and climbs until severe brain damage occurs. So if a person seems to have the other symptoms of heat exhaustion and so on, but their skin is hot and dry, then we're talking heat stroke, which is a serious medical emergency that necessitates hospitalization and immediate emergency cooling and may be fatal if not promptly treated and properly treated. So I want to just list for you here some of the personal factors that contribute to the heat disorders in addition to the various environmental and work conditions that might take place. Most of these are pretty obvious and well known. Most of our discussion is going to be about occupational exposure, but I also want to say just a few words of reminder about community heat exposure. Many deaths are associated with rapid heat waves. It seems that more often these deaths occur in northern cities in the United States where people aren't accustomed to the heat, don't have air conditioning, may not even have a proper number of fans, and the deaths are highest among the elderly and poor, probably because of security concerns where they're afraid to open their windows and doors and they don't have the resources to get away from the heat. The hazard ratings that are used are the heat index, which combines air temperature and humidity, and is usually the peak for the day. The highest temperature and humidity for the day is combined into a heat index. And then more recently, something called the mean heat index, which includes the nighttime conditions as well, and may be more predictive of the risk of death in a heat wave than simply the peak rating during the day. This listing of weather-related deaths in the United States seems to indicate that heat waves are much more deadly than various storms all combined. Of course, this is going to vary from year to year, and I don't even remember now where I got this information. It's a more subtle effect, of course, than what happens in the various kinds of storms. Sometimes I'm sure heat-related deaths are not even identified as such, particularly in people who are very elderly and sick and might have died from something else anyway. At any rate, you can see that the magnitude of the problem is pretty large. So now let's start to look at this in a quantitative sort of way, starting with the different heat gains and losses to the body. The plus and minus symbols indicate that either it's a heat gain or a heat loss. And so the metabolic heat, which is produced from the biochemical processes of doing work in the body, are always a heat gain to the body. Another source of heat gain or loss is radiation to or from objects. If the object is warmer than the body, it's a gain of heat. If it's cooler than the body, then it's a loss of heat. Conductive is also another way, or conduction rather, is another way to gain or lose heat from physically touching some object. But since most of the time that's pretty negligible of the things that we're touching, we'll neglect that from now on. Convective heat gain is either positive or negative from the motion of the air that surrounds us. It could also be water if we were in the water, but from fluids rather than from solids, as is conductive. And then lastly, we have evaporative heat loss from the evaporation of sweat, which is always a loss and helps to balance out the metabolic heat gain. We put all these heat gains and losses together in the heat balance equation, where the M is the metabolic, R is radiant, C is convective, and E is evaporative. These are all happening at the same time, and they're all simply additive. So we have M plus or minus R plus or minus C minus E equals something, X, the net heat gain or loss to the body. Now most of the time, X is 0, and the body is in heat balance. It may, for a moment or two, be out of whack, that is to say positive or negative, but over the long run, or even over a fairly short run, it's equal to 0. If X is greater than 0, then the body is gaining heat, and as it gains heat, it will increase in temperature, and that's considered a heat stress condition. If X is less than 0, then conversely we're in a cold stress condition where the body is losing heat and therefore the temperature will decrease. I'll say a few words about the units that we're going to use for temperature and heat, and to make sure that you understand the difference in the two. Temperature is a measure of the heat contained in an object, and of course we have our standard units of Fahrenheit and Celsius, Fahrenheit being the English system. We'll tend to use both of those actually, since we still commonly use the Fahrenheit system. Heat, on the other hand, is a measure of thermal energy that's contained in some body, some object, some air, water, liquid. And the two units there are the British thermal unit, BTU, and the calorie, which is the metric system unit, or it's a metric system unit. It's not the only one by any means. Start by talking about the BTU as a unit of heat measurement. The British thermal unit is defined as the heat needed to raise 1 pound of water by 1 degree Fahrenheit. Let me give you an example of how to use this. Suppose we have a heating rate for a person of 1.5 BTU per minute. This is the net heat gain. So how long will it take to increase the core temperature of a 170-pound man by 4 degrees Fahrenheit? Well, people are not water, but they're a lot like water. We're mostly water. So we can at least approximately divide the weight of the person by the heating rate to give the time to increase by 1 degree Fahrenheit. So we take our 170 pounds divided by 1.5 BTU per minute, and that will give us 113 minutes. Now you notice I didn't write the units in there because there's some funny stuff going on, but anyway, it works out. So it would take 113 minutes at this heating rate to increase the core temperature of this individual by 1 degree Fahrenheit. To increase by 4 degrees Fahrenheit, simply 4 times that amount, 453 minutes. Calorie, the metric system unit, is defined as the heat necessary to raise 1 gram of water by 1 degree centigrade, and a kilocalorie, 1,000 calories, is the heat to raise 1 kilogram of water by 1 degree C. 1 kilocalorie equals 4 BTU, and confusingly, 1 kilocalorie is also equal to 1 large calorie, or calorie with a capital C, which is our food calorie. So there's a factor of 1,000 between the food calorie and the scientific unit of calorie. Kilocalorie is what we mostly use. If we are speaking of the rate of heating, how much heat input per unit time, we could use the unit watts. 1 kilocalorie per minute is approximately equal to 70 watts, and that's a familiar unit from electricity and so on, but mostly in heat stress problems we stick with kilocalories per minute. Now let's look at the quantitative aspects of each of these heat inputs to the body, starting with metabolic heat gain. From the basic processes going on in the body, just the heart beating, the lungs pumping, and so on, we have a basal rate of heat gain of about 1 kilocalorie per minute or 60 kilocalories per hour, about the same as 70 watts. That's for a person who weighs the standard 70 kilograms. If you weigh less than that, generally speaking, you'll have a lower basal metabolic rate. If you weigh more than that, you'll have a higher rate. At 1 kilocalorie per minute, by the way, that works out to 1,440 kilocalories per day, which is food calories per day. So 1,440 calories should be just enough to keep a person alive, assuming they were just lying in the bed doing nothing. And another way that I find interesting to think about this is if 1 kilocalorie per minute is about the same as 70 watts. So imagine yourself lying in bed just completely still, covered with a blanket to hold in the heat. And so you know it gets warm under the blanket just from your body heat. That's about the same heat as you would get from a 70-watt light bulb under there. Additional heat gains from actions that the body takes are listed here. So standing up requires an additional 40 kilocalories per hour to your basal rate. Not much, but somewhat more. Walking on the level, about 150 kilocalories per hour, again, depending on how fast you walk. Light work, like with your hands or arms, additional 100 kilocalories per hour. Heavy work, 200 or more. And again, these need to be adjusted for weight. Our standard person is a 70 kilogram man, so if we take our weight of the actual person and divide by 70, then multiply times the normal rate, we'll get the more or less the actual rate. I'm sure that people vary in their basal rate as well as in their rate when they're doing various activities, but these are the numbers that we're going to use. When it comes to controlling metabolic heat output, there's nothing we can do about the biochemical processes in the body. We can just change the work. So obviously, various task modification ideas such as slowing down the pace, having smaller loads to lift or deal with, mechanized to some extent to let machines do the work instead of the human body. Those are all possibilities. I'm sure you can think of others. If those aren't possible, then we can think of work-rest schedules, either informally or formally. If the person gets tired, they can stop, take a rest, if it's for a few minutes or a longer period. Or if that, again, is not possible, then you have steady work for some period of time and then mandatory rest breaks. We'll be talking about that when we discuss the occupational exposure limit for heat stress. Let's look at the factors that influence convective heat transfer. Key point here is the difference between air temperature and skin temperature. If the air temperature is greater than skin temperature, there's heat gain. If air is less than the skin temperature, then there's a heat loss. Skin temperature is not so easily measured as air temperature, so we assume that in a heat stress condition, skin temperature is going to be 95 degrees F, 35 degrees C. Ordinarily, with the body in a heat balance condition where there's not a stressful situation, it'll be somewhat less, but for purposes of the calculation, we'll use 95 degrees F. The other factor we have to keep in mind is air velocity, which influences heat transfer by stripping away the blanket of air that surrounds the body that has been influenced by the body heat. So if the air is cold, the body will warm up a thin layer of air near the surface, and moving air takes away that warm blanket. So higher air velocity, at least to a certain extent, increases convective heat transfer, whether it's a gain or a loss. Please write down and remember this number for participation grade purposes. The number 15. Let's look at the quantitative calculation of heat loss or gain from these two factors, the skin air temperature difference and the air velocity. So we have two equations depending on whether we're looking at the metric units or the English units. In both cases, we have velocity to the 0.6 power, which means just slightly greater than the square root of the velocity multiplied by the air minus skin temperature. So if the air temperature is greater than skin temperature, C is going to be a positive number, heat gain. If air temperature is less than skin temperature, then C will be a negative number or a loss. Don't worry about the units here. Just make sure that when you're doing the English ones, you're talking feet per minute and degrees Fahrenheit, and you'll get BTU per hour. When you're talking metric, you use meters per second, degrees centigrade, and you'll get kilocalories per hour. With this in mind, let's look at the convective heat controls that are a possibility. The first one that comes to mind is the air temperature, which can be influenced by either dilution ventilation or by mechanical air conditioning. Dilution ventilation is used commonly where there's a very hot process like a furnace and the outside air is cool enough to bring the temperature down. Many processes these days use mechanical air conditioning either for the whole room or sometimes just as a spot cooler right on the individual. More common is a spot cooling fan to increase the air velocity, but you always have to keep in mind that air velocity is a way of increasing heat gain rather than increasing heat loss if the air temperature is high enough. So only if the air temperature is less than 95 would you want to use spot cooling fans. Clothing is another obvious way to control convective heat transfer. If the air is cold, we put on more clothes, and if the air is warm, we take off clothes. This can all be figured quantitatively. There's something called the CLO, C-L-O, which is a unit of clothing insulation, but I don't want to go into that detail, so we'll just consider the common sense approach of more clothing equals less convective heat transfer. Now let's look at radiant heat transfer calculations. For this, we have to note the wall temperature surrounding the individual. Obviously, if you're standing next to a furnace, the furnace wall is going to influence radiant heat gain or loss, but there are also other walls or maybe even open air surrounding you. So you have to use a weighted average of whatever surfaces are surrounding the individual. Weighted, by weighted I mean surface area weighted. Then to do the calculation, it's simply a matter of the difference in the wall temperature and the skin temperature. And just like with convective heat or loss, we look at the difference, and if the wall temperature is higher than the skin temperature, then it's a gain. Otherwise, it's going to be a loss. So we have two equations here, one for metric and one for English unit. You may read somewhere that it's actually a question of the fourth power of the wall-skin difference, but this is an approximation that's close enough for most purposes. Control of radiant heat transfer can be done in several ways. One is by modification of the wall that's emitting heat. Simplest, most obvious way, I guess, would be insulation to lower the surface temperature and keep the heat inside. So that's usually done to the extent that it's possible. Another control that may not seem quite so obvious is what's known as emissivity control. A shiny surface has low emissivity, by which we mean low efficiency of heat transfer. A dark surface has high emissivity and therefore radiates more heat. So very often hot objects are enclosed with a shiny metal skin of some sort. We can also modify the path between the person and the hot surface with some sort of a shield. Very often a sort of a mesh shield is used that will absorb a lot of the radiant heat while still allowing air to flow through. And then lastly, we have clothing, which can shield the person in that sort of way also. Next, we'll look at evaporative cooling. This is a little more complicated than the others. It involves the heat loss that occurs when a liquid changes from the liquid state to the gaseous state or water vapor. This is energy that's stored in the vapor as the bonds that hold it together are broken. So without changing temperature, as a milliliter of water goes from the liquid state to the vapor state, it requires 0.58 kilocalories. That's per milliliter, so that's 580 kilocalories per liter. This is a large amount, actually, 580 kilocalories per liter of sweat. But one of the basic limitations is how much can a person sweat. And this would be, at the most, about 1 liter per hour, or 580 kilocalories per hour. That's considered the upper limit on the evaporative cooling. For a person who doesn't have enough liquid in them, who's dehydrated, or who's not acclimated to heat, they may not be able to sweat at this rate. for our calculations, we use 580 kilocalories per hour as the limit on evaporative cooling. Besides the limit imposed by the amount that one can sweat, there are other limits, one of which is the amount of moisture in the air expressed as humidity. When the air is completely saturated with water vapor, we say that it's at the saturation pressure, and so the vapor pressure of water is expressed in so many millimeters of mercury of pressure. Now this varies with temperature. Warmer air can hold more moisture, so the saturation pressure goes up with increasing temperature. We're usually not at the saturation pressure. We're not completely saturated, so we express that in terms of the relative humidity. So if the relative humidity is 50%, for example, that means we're at 50% of the saturation pressure. If the saturation pressure at a given moment is, let's say, 30 millimeters of mercury, and we're at 50% humidity, then the actual pressure, or the absolute humidity, would be 15 millimeters of mercury. You'll see how we'll use this in a few minutes. Another factor is the air velocity. Just as with convective heat transfer, evaporative heat transfer is affected by air velocity because as we sweat and as that sweat evaporates, it creates a tiny layer of saturated air around our body, which inhibits further evaporation. Moving air strips away that saturated layer, allowing better evaporative cooling. And then, of course, clothing has an effect. The calculations that we're going to use are for normal clothing. If you have impermeable clothing on, such as might be used for hazardous waste operations, then the air inside the clothing becomes saturated very quickly. The air velocity, or the moving air, can't get to it to do anything about it, and so all the sweat just drips off the body and fills up your boots, and you get no evaporative cooling. Here are our equations for evaporative cooling calculations. You'll notice that they're very similar to the convective calculation in that we have the air velocity to the 0.6 power. Instead of a temperature difference, however, we have a pressure difference, where P sub A is the partial pressure of water vapor in the air, and P sub S is the pressure at the skin. And again, we have two different equations depending on whether we're looking at metric units or English units. The partial pressure of water vapor in the air is determined by the relative humidity and the air temperature. At the skin, we assume that the skin is at 95 degrees Fahrenheit, 35 degrees C, just as we did for convection. And we assume that the skin is thoroughly wetted, so the air is saturated right at the skin, and therefore we use the saturation pressure of water at 95 degrees F, which is 42 millimeters of mercury. So you don't have to do any calculation or measurement on that. You just always plug in 42 millimeters of mercury for P sub S. Now P sub A, the partial pressure in the air, will always be less than that. So E, well, if there's any heat transfer going on, it will be less than that. So E will always be a negative number. Here's a chart showing vapor pressures, or saturation pressures, of water vapor at various temperatures. Keep in mind these are fully saturated pressures, so the actual partial pressure is this number multiplied by the relative humidity. So for example, at 29 degrees C, the vapor pressure, or saturation pressure, is 30 millimeters of mercury. If we had 70% relative humidity, we'd take 0.7 times 30, or 21 millimeters of mercury, would be the partial pressure of water vapor we would use in our equation. How do we increase evaporative heat loss? Well, you'll notice that most of this is about the same as the convective heat loss considerations in terms of ventilation and air velocity. One significant difference here is clothing, and particularly that in dry environments sometimes the clothes can be wetted, so that it's not just sweat that's causing the heat loss, but also the evaporation of water applied to the clothes. Obviously, in more humid environments, this wouldn't really do any good, and the other measures, particularly the mechanical air conditioning to reduce both temperature and humidity, would be more effective. There are various environmental measurements that we can use as indicators of heat and cold stress. In particular, the one that's used most often for heat stress is the wet bulb globe temperature, WBGT. Some other environmental indices would be the effective temperature, which is calculated slightly differently, the heat index, which is used for community purposes, also the mean heat index, which include both humidity and temperature, and then the wind chill index, which would be used for a cold stress indicator. These are generally screening indicators. If they're exceeded, then one may need to do heat strain measurements. The distinction between heat stress and strain is that heat stress are the conditions which may cause harm. Heat strain is the bodily response to the stress conditions. So when we measure body temperature, for example, we're checking to see if there's heat strain taking place. What are the elements of measurement of the WBGT? Well, first we have the globe temperature, which is simply a measure of the radiant heat. A thermometer is put in the center of a black globe. Black absorbs radiation, so that's a measure of radiant temperature. Then there's the natural wet bulb temperature, which is a very clever way of measuring all three elements: air temperature, humidity, and air velocity. By using a wick covering the bulb of the thermometer, which is wetted with distilled water, as the water evaporates, it cools the bulb of the temperature, and this is called the wet bulb depression. So the thermometer is measuring air temperature, but then it's also measuring humidity because of this wet bulb depression factor. And then, of course, the water evaporates more rapidly due to higher air velocity, so it's also indirectly a measurement of air velocity. So it's called natural wet bulb. You may hear about wet bulb otherwise, and that's usually referred to what's more specifically called aspirated wet bulb, where the thermometer is moved rapidly through the air, or air is mechanically blown over it to determine the relative humidity. But this one is the natural wet bulb, so there's no artificial movement of the air. Then lastly, there's the dry bulb temperature, which is just the ordinary air temperature measurement that we're normally accustomed to. So then we turn to the calculation of WBGT, and it's just a very simple equation which has two elements, one for shaded environments where there's no direct sun exposure, and then another different equation if there is sun exposure. So WBGT is 0.7 times the natural wet bulb temperature plus 0.3 times the globe temperature for the shaded environment. So we're putting most emphasis on the natural wet bulb. In the sunlight, we also add the dry bulb temperature. It's possible to make up a simple group of instruments to measure WBGT, globe thermometer, wet bulb thermometer, and dry bulb thermometer, but very often these days they're done with electronic instruments. The two instruments pictured in the center are for measuring WBGT. The one on the second from the left, for example, is a dry bulb thermometer on the left, globe thermometer in the center, and a natural wet bulb thermometer on the right. The cup houses the wick, and there's a water supply there to keep it wet. The two instruments on the outside are for measuring heat strain, that is to say, measuring the effects on the human body. The one on the far left you can see most easily has an earplug with the thermometer inside it, so you insert that into the ear, and it's measuring the temperature inside the ear canal with it sealed to prevent influence from the outside air. So this is a pretty good approximation of body core temperature, and the instrument can be set to sound an alarm if the core temperature gets too high, or to provide a data logging function so you can monitor the human response to the hot environment. We've mostly been talking about environmental measurements, but now let's talk more about heat strain that we alluded to in the one about instruments. It only takes a small increase in body temperature to indicate heat strain effects. If 37 degrees C is normal, then 38 degrees C would be the upper limit of normal. So 1 degree C, or about 2 degrees F, is the maximum we should tolerate. Another degree centigrade up, and we're at a 25% risk of heat exhaustion, and greater than 41 degrees C, there's a high risk of heat stroke. How does one measure this? Well, traditionally, for research purposes, the rectal temperature has been the standard way of measuring core body temperature. Oral temperature can be done, but it's not quite as reliable. Neither one of those are particularly convenient, of course, for field usage. So the oral temperature is sometimes used, as in the instrument we saw in the last slide, where the ear canal temperature is supposed to be a better indicator of core temperature than the oral temperature. But either one can be used. There are other physiological indicators that are often used as well for heat strain, one of which is heart rate. You see different sorts of recommendations, but a couple that I've run across are that during the first minute of rest following the peak work period, if the heart rate is greater than 110 beats per minute, then that indicates excessive strain and additional rest should be mandated. Or alternately, greater than 90 beats per minute during the third minute of rest after the peak work period. Sometimes there's also measurements about what the change from the first minute to the third minute is. If the heart rate is not going down fast enough, that indicates problems. Water loss is also indicated as a heat strain indicator, with greater than 1.5% being the threshold of dehydration. So you sometimes see the recommendation that the person be weighed at the beginning of the work shift and the end of the work shift, and if they've lost more than 1.5% of their body weight, then they haven't been drinking enough water, they're being dehydrated. Other indications are listed here. 4 to 5% water loss leads to heat exhaustion, and greater than 7% is a strong risk factor for heat stroke. There are some occupational exposure limits for heat stress. Although OSHA doesn't have one, they use the general duty clause. As far as I know, they've never really seriously considered looking into developing their own exposure limit for heat stress. The ACGIH threshold limit value combines the WBGT and work activity as a screening method to determine the work-rest schedule. Or alternately, you could look at the combination of the work-rest schedule and the other factors to see if there's a possibility of heat stress, at which point you institute heat strain measurements. NIOSH has a number of recommendations on this, but the one that I'm focusing on here is an alternative to the ACGIH TLV, which is for workers wearing normal work clothing. And the NIOSH limit is for workers with impermeable clothes, such as are used in hazardous waste sites, which combines solely the temperature and the solar load to determine a recommended frequency of monitoring for heat strain. Please write down and remember this number for participation grade purposes, the number 4747. So here's the screening table in the TLV for heat stress. This is kind of complicated, so let me point out a few things on it to you. First off, the red numbers at the top are for acclimatized workers, and the ones at the bottom, the black numbers, are for unacclimatized workers. So you see there's a difference in how much work is allowable at different temperatures for these two different sets of workers. The whole idea of this table is that if one follows these rules, then the core body temperature for most workers should not exceed that 38 degrees C or the 1 degree C rise, which is the upper limit of normal. If one exceeds this level, then heat strain measurements need to be applied. So for example, if a person is doing heavy work, and the kind of work will be defined later, and the temperature is 27.5 degrees C, then there should be no more than 75% work and 25% rest. If the temperature goes up by 1 degree and the person's doing heavy work, so now we're at 28.5 degrees C, and we're talking about acclimated workers, then the workload changes to 50% work and 50% rest, and so on. Oh, I should point out that the WBGT here is assuming that the work and rest areas have the same thermal conditions. If they're different, if for example the workers rest in a cooler environment, then a time-weighted average of the work environment and the rest environment should be used to determine the WBGT to be used in the table. Some example work descriptions to be used in this table. These come from ACGIH, and I won't read these to you, but you see the kinds of descriptions. Of course, every work is a little different, so you have to make some judgments about what is light, moderate, heavy, and very heavy. An alternate approach to looking at this is to measure or estimate the kilocalories per hour and then fit them into these categories where light is up to 249 kilocalories per hour and so on. Before I discuss that you have to use weight adjustments when figuring metabolic heat rates. Also, age adjustment can be done. The TLV was originally based on data for young men, Army recruits, according to this source that I've found. So one has to use an age adjustment to correct this work rate for different kinds of works. So the metabolic rate for standard tables is divided by the correction factor to find the actual metabolic rate for different ages. And again, to remind you, the weight correction is based on the 70 kilogram person. If the person weighs more or less, then you have to adjust that as well. Here's an example calculation to show you how some of this works. First, we take all the different activities that the person is doing and compute the total metabolic rate, being sure to add in the basal metabolism of 60 kilocalories per hour, the posture factors, either standing or walking. In this case, the person is standing for 2/3 of the time and walking for 1/3 of the time, so you make an adjustment for that. And then they're doing light work with both arms. You add it all up and it's 224 kilocalories per hour, which, because it's less than the 249, is light work. But we have to look at our weight and age corrections. So if this was an 85 kilogram person, we would correct up to 272 kilocalories per hour, which moves it from light to moderate. And if they're 50 years old rather than 20 years old, an age correction factor also must be applied, moving them up into the heavy work category at 349 kilocalories per hour. I should stress that the TLV book does not actually say to do this, but it seems reasonable to me. The TLV is based on protecting most people, but we also have to consider personal factors when we consider the actual heat strain that may result from any given heat stress. We've already discussed acclimatization, which is adjustment to working in heat. The physiological effect of acclimatization is that a person will be able to sweat more, and the sweat will be more dilute, so they'll lose fewer minerals, less salt in their sweat, and so they'll be better able to work in heat. The only way to become acclimatized is to actually work in hot conditions. Even if you're physically fit otherwise, you won't necessarily be well acclimatized. It usually takes at least 1 full week of working in the heat, although more time is better to become fully acclimatized. The general recommendation for unacclimatized workers is that when they first start working in the heat, one uses only half the normal work for that first day and then adds 10% for each subsequent day. Other health factors are listed here, such as metabolic disorders like diabetes. Previous heat injury, particularly heat stroke, predisposes a person to heat stroke again, and factors such as alcohol and drug use may decrease heat tolerance. The factor to keep in mind when looking at the TLV is the level of clothing. The TLV is based on summer work clothes, which is long pants and short sleeve shirt. If you're wearing less clothes than that or more clothes, you can adjust the WBGT to account for the clothing. The first 3 items on here are from the ACGIH. The last 2, the winter work clothes and the Tyvek full suit, are from other sources. And I'm, even though I put it on there, I'm a little dubious about the Tyvek one, because the WBGT really becomes fairly meaningless if you have a suit that's relatively impermeable to moisture, since you aren't going to get any benefit from evaporative cooling after a very short time. The NIOSH recommendation for workers wearing impermeable clothing, like in hazardous waste work, is for acclimatized workers doing light to moderate work. It's based on something called the adjusted temperature, which is the ordinary dry bulb temperature taken in a shaded location, plus 13 times the percent sunshine. So if there's no clouds in the sky and the sun is shining, then it would be the dry bulb temperature in Fahrenheit plus 13 degrees. Then you take that adjusted temperature and use it to determine when to do physiological monitoring for heat strain, whether that be temperature measurement or heart rate measurement, or I guess body water loss. So if the adjusted temperature is less than 77.5 degrees, you're supposed to monitor after 120 minutes of work, and so on, up to greater than 90 degrees, where you have to monitor every 15 minutes. Let's look over the different kinds of controls. We've already talked about most of these, so this will be mostly a review. On the engineering control side, one might consider it the source control of heat stress. We have metabolic control, which would be mechanization of the work and similar changes to reduce the workload, and environmental changes, temperature and humidity, air velocity if appropriate, radiation control, whatever is needed based on the specific kind of job. This, of course, is, as always, is the recommended method. Do the engineering control before doing the other steps. Next in the hierarchy of controls comes administrative controls. And these are pretty much common sense. Work during the coolest part of the day, for example, is one that's very often done. A lot of construction work, for example, and other kinds of outdoor work rely on this. One might also need to implement a work rest schedule. Ordinarily, for many jobs, you can allow a natural pace. If people are well motivated, they will get their work done, but give themselves breaks as needed when the heat is too much. If it's the sort of work that doesn't allow that, or if the workers are too well motivated, for example, if they're on a piece rate or something like that, you might need to schedule breaks based on the TOV or something similar. Training on heat stress and strain would be another example of an engineering control, as would instituting some sort of co-worker observation. If workers or supervisors are trained to know the signs and symptoms of heat strain, then they can intervene if necessary. Under receiver control, we might consider water and salt replacement. Requiring good water consumption is critical to a heat stress control program. It's generally considered that most people don't drink enough water, just driven purely by thirst. So if you know people are going to be working in stressful conditions, they should be encouraged to drink plenty of water before they start work and be given ample water breaks. Make sure they have good-sized cups and water that's not too cold, not too warm, so it'll be highly palatable. Previously, salt tablets have often been used in heat stress conditions, but that's generally not recommended. Now most people get plenty of salt in their diet, particularly once they're acclimated to the heat. They really don't need salt replacement, although it might be useful during the pre-acclimation period. Special drinks like Gatorade and Powerade and these sort of things that have various electrolytes in them might be helpful, not so much in replacing the salts, but because they're perhaps more palatable and attractive to drink. Other elements of receiver control, as listed here, would be medical evaluation of some of those personal factors we talked about, acclimatization, heat strain measurement like measuring temperature, heart rate, or water loss, and then lastly, personal protective equipment, which we'll discuss in the next couple of slides. Here's an example of a personal protective piece of equipment, a cooling vest that has space in it to put ice or real cold water, or sometimes they even use dry ice. These may work for a period of an hour or up to a few hours. There are also helmets that have ice in them or that can circulate cold water in them to help with very stressful conditions where a person can't simply use the work rest schedules. Picture of something called a vortex cooling vest. The key thing here is that you connect it to a compressed air line shown where the red arrow is, and the vortex cooler takes this high velocity compressed air and it's configured in a way so it spins around, and by something that's a little short of a miracle in my opinion, the hot air comes out one side and cold air comes out the other side. So the hot air goes out the front, just discharges into the atmosphere. The cold air is going into the back and into this vest, so providing a cold vest all the way around this guy. Of course, you have to be hooked up to a compressed air line, but then you have continuous long-time cooling, which works very well. I don't know what these cost, but they're very effective. Please write down and remember this number for participation grade purposes, the number 7171.